So on this slide we talk about direct limits and give some examples. So to understand direct limits or co-limits, we need to understand the concept of a functor, and this is not explained here, but you should know about what a functor is. So we start with some set S. So say S is a fixed set, and we call S a directed set, and it is a set which is partially ordered set. So it's a directed set, that is a poset, a partially ordered set. And whenever you think of a poset, you should always keep an example of integers in mind. So integers are ordered, and such that for all AB in S, there exists C which is also in S, such that C is greater or equal to A and C is greater or equal to B. So simple example as I've given is integers or any subset of integers. So you have set S, and then you have abelian groups. So set S is partially ordered. So you have relations like S is less than equal to T. So for S is less than equal to T, you draw an arrow from S to T. So that relation is captured in the arrow. In the abelian group, you have standard abelian groups. So you will have one group AS and another group AT, and these correspond to elements S and T in the set S. So you apply a functor D, then you land from partially ordered set to abelian groups. So relation S is less than equal to T converts into a group morphism in the category of abelian groups. So notice two things. You have an order here in category S, and that order is essentially carried over to abelian groups. So again, for directed sets, you should always think of integers as the crutch to understand what is going on. So this functor D is called the directed system of abelian groups. So you just had a bunch of abelian groups, and then you put an order onto them. So for example 1, 2, 3, 4, and then you put order onto abelian groups A1, A2, A3. You had a bunch of morphisms going on to them. So you from any abelian groups and their morphisms, you made a directed system out of it. So you now have a system. So the direct limit is an abelian group. So you should think of direct limit as nothing but a abelian group. And this abelian group is such that so I will write this down. So first, this is the symbol for direct limit. So you are talking about direct limit. This is how you write it, where D is the functor which goes from directed set to abelian groups. So you think of it as a disjoint union of all the abelian groups you have. And then you modulo out by some equivalence relations. So we need to figure out what this equivalence relation is. So this equivalence relation essentially means that you take two elements, say A is in abelian group AS and B is in abelian group AT. So these A and B are equivalent or identified together. So this A and B are equivalent or identified together in the direct limit if they are same in some group AU, and the subscript of AU, that is U, is important. U is greater or equal to S and U is greater or equal to T. So let us write this down. So if there exists some element U in the directed set S, then U is greater or equal to S, U is greater or equal to T. So there is an arrow from S to U and there is arrow from T to U. and A and B have the same image in AU. So you should think of it in terms of stalks. You're taking smaller and smaller neighborhoods, and in the end, two functions should agree in a tube. So like we discussed in the previous lecture, a tube around 0, so they agree in some neighborhood. So let us draw this pictorially. You have an arrow going from S to U, you have an arrow going from T to U. So obviously you apply a functor D and you have some abelian groups, you put the system onto those abelian groups. So you put the system of these arrows on abelian groups. So you have an arrow from AS to AU and AT to AU. We have an element A in AS, B in AT, and these elements via some group homomorphism will get mapped to AU. But in AU, they get mapped to the same element. So basically, when we talk about a stalk, I am saying in that small neighborhood, that tube around 0, these two elements are getting mapped to each other. Two functions are getting mapped to each other. And that is precisely what we are writing here. We are taking the smaller and smaller neighborhoods. Those smaller and smaller neighborhoods is what? Is AU. So AU is that smaller and smaller tube around 0. So we can similarly talk about direct limit of rings, modules, etc. So I will repeat again, we have already drawn one of continuous functions around 0. So suppose sometimes it is given like this, there are a bunch of group homomorphisms. So you have Z, then the morphism is multiplication by 5. So you just have these group homomorphisms. And you are asked to find the direct limit of these group homomorphisms. So first thing is you want to find what is the directed set involved, and then you can talk about how the abelian groups actually look like. So directed set is 5 less than equal to 5 square, which is less than equal to 5 cube, and so on. So this is the directed set involved. Now we want to talk about how would the corresponding abelian groups look like. So you have to take into account this 5 square, 5 cube, and so on. So it actually looks like Z embedded into 1 by 5 Z. That means all integers with the denominator 5 plus all integers. This is embedded into Z 1 by 5 square. That means all integers plus all integers or rational numbers with denominator 5 and plus all rational numbers with denominator 25. So the direct limited is Z, instead of Zx I am writing Z 1 by 5, so all integers and then all rational numbers with the denominator 5. So so Z is embedded into 1 by 5 Z, which is integers plus, so it is just building up, Z 1 by 5 cube is integers plus all rational numbers with denominator 5, all rational numbers with denominators 5 square, all rational numbers denominator with 5 cube. Similarly, Z appended with 1 by 5 4. So more generally, if you have multiplication by F, you get R appended with 1 by F. So what you get is, so you have the directed set F, F square, F cube, and so on. So R is embedded into R 1 by F. That means R 1 by F consists of a copy of R and then rationals with R as the numerator and F as the denominator. R 1 by F square is, it has copy of R, it has copy of R 1 by F, and it has additionally a copy of R 1 by F square. So R 1 by F square has R, then rationals with R numerator, F denominator, then R numerator and F square denominator. So again you write it like this. So this is clear. So let me be clear. So it is G by Fn, where G is the element of the ring and n is greater or equal to 0. So these were very important examples. Another example is, So let f be a constant presheaf. By constant presheaf we means that, for example, for any open group U, f of u say is integers. So it's a constant presheaf. So for any open U, you have, so you first fix a topological space X, and for any open U in X, f of u is integers. Yeah, and all the morphisms are ID. Yeah, so you will always have morphism from Z to Z. So if V is a subset of U, f of V is also integers, and the morphism is ID map. So then stock of f at every point X is also integers. So we have fixed a topological space X. We are considering open sets U of X, and we want to find stock at point X, and we are saying here in case of constant presheaf it is just integers. So let us draw it out. So this is what the space X looks like. And at different points we have the stock of integers. So at x1 we have integers, x2 we have integers, x3 we have integers. So we have f of x1 here. So this entire topological space is X, and so on. So on this slide we give an example of stock. So we cover a very fundamental example. You first fix a space X. X is algebraic set over K, and OX is sheaf of regular functions. Then you take a small point X in this big space X, and we want to determine what is the stock at OX comma X. Yeah, so we take a small point X in the capital letter X, so small letter x in capital letter X. So what is this? So this is what we want to determine, where the small x is a point of the space X, where X is algebraic set over K. So you start by taking a affine open neighborhood of X, and you say this set is U. So you take an open neighborhood of X and you call that open neighborhood as some set U. So say it is U. And obviously once you have a set U, you already know the ring O of U on it. So you have the ring O of U, then you fix an element F in O of U. So O of UF is O of U and then 1 by F. Yeah, so let us draw this. So you have the set X in this set U. Yeah, so see it is U, there's one finite point which is missing, so that it is an open set. So I've taken one point out. Now you have a function F which is in O of U. So this F is in O of U, it cuts at 4 points. So U of F will have these 4 points missing. So this is U of F, and OU of F is, you started with the ring OU. OU we have discussed many times, and O of U, then you append to it 1 by F. So O of u is obviously, it could have been cut by some other polynomial function, and we have already seen the construction process how to get O of u before. So again notice that f of x is not 0 on u of f, because we have basically taken out the points out of u where fx is 0. So that is why f of x is non-zero at x elements of u of f. So you have this open neighborhood of x in u. So every open neighborhood of x in u it contains uf for some f in O of u. So obviously uf is a subset of u, as you see in the figure above. Yeah, with f of x non-zero. So now you have constructed a sequence of neighborhoods. So one neighborhood is contained in the other. Now you can take another function g and try to cut it in u of f, and you will construct another set inside u of f. So you have created this directed set which is ordered by inclusion of open sets. So corresponding to those sets, so you have f of x is not 0, so you had this sequence of neighborhoods. Because of those directed sequence of neighborhoods, you fixed corresponding abelian groups, that is O u of f or rings O u of f, and therefore you can see how to take the direct limit. You can stop here and see what I'm talking about. What is a directed set? Directed set is inclusion of neighborhoods. What is the corresponding abelian groups or rings? Those are O u of f. That is it. So we have two different things. On the one side we have directed set of inclusion of neighborhoods, and the other side we have the corresponding ring morphisms. And this is the direction. F is less than or equal to g if g is a multiple of f. So this is important. F is less than or equal to g if g is a multiple of f. This is used in the ring part. So basically, what is Ox comma x? So it is of the form g by h, where g and h belong to O of u and the denominator is non-zero. So that is it. So the denominator is non-zero. So this I am marking in red. Notice that g is a multiple of f is a necessity for decreasing neighborhoods. So basically the answer is in red. So if anything comes up, you just need to think of it. Just rational functions in the open set, and you just take it of the form of g by h, where h is non-zero at x. So this is very important to know. What is a stalk at a point? Just some rational functions whose denominator does not vanish at that point. And it's just commonsensical now once you look at the answer that is what you wanted it to be anyway. So this Ox comma x is called the local ring of this space x at this point x. So I'm just going to show you again this. Suppose the space x, which is an algebraic set in the form of a circle, you have a bunch of points on it, x1, x2, x3. Corresponding to each point we have a local ring. So we have a ring associated with it. Again, it is just a bunch of rational functions where the denominator does not vanish at the point. So again, functions of the form g by h at Ox comma x3, where h of x3 is non-zero. Similarly at x2, so g by h where h of x2 is non-zero, and so on. So we now give a definition of a local ring. You can see why we call it a local ring, because point x1, x2, x3 are just local. So a local ring is a commutative ring R with one maximal ideal. So this is the commutative algebra definition. Yeah, equivalently we can say that all non-units in ring R form an ideal. So the question is, what is this maximal ideal of our local ring OX comma X? So this maximal ideal, again, OX comma X is of the form G by H. Yeah, so the maximal ideal you can say where G is 0. So if you write maximal ideal is say mx, so the functions in mx are precisely those functions, say they are functions f in mx, such that those functions vanish at the point x. So for example, at x3 you have the ring OX comma x3. So the maximal ideal of the ring OX comma x3 is all those functions which have f of x3 equals to 0. Similarly for x2, similarly for x1. So m of x definitely belongs to O of x comma x. I'm not sure if it belongs to O of u, but yeah. So you should take the second sign with care. So mx is the only maximal ideal in OX comma x. So this you can see, if a function is not a part of m of x, that means f of x is not 0. So that means 1 by f is part of the ring. So this is not an m of x, that means f is not 0 or g is not 0. So then 1 by f, which is h over g, is in OX comma x. Yeah, that is, only the units are out of the maximal ideal. Basically because we take all fractions, that's why we have the maximal ideal, and the maximal ideal is precisely all those functions which vanish at that point. So on this slide we talk about field of rational functions and we construct it via Stalks. So let x be a variety over k, then the field of rational functions. So yeah, the rational function is precisely you take the ring and make rational functions out of it. So obviously you have a ring OX and then you take the fractions, make fractions out of OX, and you get the ring of rational functions. So now we are trying to just give it justification in terms of Stalks. So again these rational functions are made from the ring OX. So you take, obviously now we have to take direct limit over some directed set, and the directed set are just the open sets in X. That is pretty much it. So yeah, so non-empty open sets are dense, and thus we have non-empty intersections, and we use these intersections precisely to form direct limit. So you can start constructing O of u using any functions f1, f2, f3 from the ring O of x. So basically you just keep on taking functions out of it, keep on forming open sets, taking their intersections and take direct limit, and you end up getting the fractions of O of x. So notice that functions on k of x may not be defined everywhere. So let this f be element of k of x, it may not be defined everywhere. Yeah, but they are defined in some neighborhood. So again, k of x is you just take the fractions of everything possible. So I've said before, k of x is fractions of ox, but you can also think of it as fractions of ou. So you take fractions of ou for all u open in x. So for example, you say f is g by h of x might vanish at some point x, but h of x might not be 0 in some neighborhood, and there we can define f as g by h. So again I will say k of x is nothing but, either you think of it as fractions of ox or you think of fraction of ou, and you take all open sets of x, because after all ou you also construct out of functions in ox, so it wouldn't make a difference. So first example is k of an is just k x1 x2, so this we have seen before. More importantly, k of pn is also k of an, and this we need to see. Now obviously the projective space is covered by open sets, and now we have to talk about each open set, what is happening. So we want to define on each open set. So see, you have the definition, you have direct limit over every open set, and as I said before, k of x can also be considered as fractions of O of u for all open sets. So we see that Pn is covered by open sets a0, a1, a2, a3, all the way to an. So k of a0 is you take 1, because you fix the first coordinate as 1, first coordinate is non-zero, and then you have 1 comma y1 all the way to yn. K of a1 you fix the second coordinate as non-zero, so you have y0 comma 1 y2 all the way to yn. Then k of a2 you fix y2 as 1, so you have y0 y1 1 all the way to yn, and so on. So as you can see, each of these is same as k x1 to xn, because you are fixing one of the coordinates as 1. So this is important to know and understand, that how we are taking fractions over each open set. So the direct limit is formed by fractions over each open set, but it also we can take the previous definition also into consideration as fractions of O of x. So now we quickly talk about birational. So two varieties x and y are birational if kx is isomorphic to ky as field extensions of k. So let us write this down. So k of x is iso to k of y as field extensions of k. If and only if. So now we are talking about when are two varieties birational. So two varieties are birational if some non-empty open subset of x is iso to some non-empty open subset of y. So you can check the definition of birational, and you will see it just consists of rational functions and their inverses. So we have already talked about polynomial functions from one variety to another. So instead of polynomial functions, we are considering rational functions to go from one variety to another. So let us draw a figure. So notice that, say this is variety x and we take an open set of it. So we delete 2 points. So we can only delete a finite number of points for getting open set. Take another set y, you take 1 point out of there, and yeah, so these two non-empty open sets are the same or iso. Then we have x and y are birational. Second, you can see an and pn are birational because you just take one open set of pn. It is same as an. Fact 2. So let x and y be algebraic sets over K. So x and y are algebraic sets over K, and you fix points x and y. Yeah, so you fix 2 points x in x and y in y. So let us write this down. You fix a point x in x and y in y. Yeah, then these K algebras ox comma x and oy comma y are isomorphic if some small neighborhood of x is iso to some small neighborhood of y. So basically two rings are isomorphic if the neighborhoods are precisely the same. Yeah, again these two rings are defined at a particular point, but they are really dependent upon small tubular neighborhood around them. Yeah, as we saw in the construction of a stalk around 0 in the previous lecture. So these two are iso if they agree on some open neighborhood. So they are iso on some neighborhood.